Okay, welcome everyone, and thank you for joining us this afternoon for our virtual event. My name is Jean-Michel Laurent from Under Technology, and I'll be your host for today's presentation. Today, we are talking about the impact of stoichiometry on the photophysical properties of Ruddlesden-Popper perovskites. I'm joined today by Professor Maria Loy. Maria Loy is professor at the Zernike Institute for Advanced Materials of the University of Groningen and is chair of the Photophysics and Optoelectronics group. Welcome, Maria.
Thank you very much, Jean-Michel, for the kind introduction.
Just some indication before we get started. You have all joined this presentation in listen mode only. If you have any questions during the presentation, please type them into the question box in the control panel as we go along. Questions will be answered at the end of the presentation. And now, without further ado, I will hand over to you, Professor Maria Loy.
Thank you very much again, Jean-Michel, for the kind introduction. And welcome everybody to this presentation. So today I would like to speak about a new class of materials that has been investigated in the last 10 years very intensively for applications in photovoltaic. However, I will give it to my presentation, of course, a spectroscopic touch, and I will investigate a special problem we have seen in these systems. So let me first introduce the class of material. I'm speaking about metal halide perovskite. And in particular, I want to introduce you to the formamidinium lead iodide. This is a semiconductor that has a band gap of about 1.48 electron volt. It has a very good thermal stability compared to other type of metal halide perovskites. It displays low hysteresis when you make photovoltaic devices. And it shows very high power conversion efficiency. Just to give a number, the record efficiency is obtained with this specific material, and is nowadays 25.5% in a single junction device. Just to give you an indication, so we are only below 0.6% far away from single crystalline silicon record. So in 10 years, actually, we did with this class of material what people did in 40 years with silicon. Why this material is so successful? Because it has a very good band gap for photovoltaic devices. As you can see here, is precisely on the maximum of the shock liquizer limit. However, the material has some little problem. So it's structurally unstable. It tends to convert from the black phase, the alpha phase, that is the one of the perovskite that we are interested in a yellow phase that is not a perovskite material, and also called the delta phase. So now, in the literature, there have been reported several strategies to stabilize this black phase. And I showed just a few examples. One of them is reported in this paper, actually has been to introduce some two-dimensional type of perovskites into the three-dimensional phase. And these mixtures, actually, they show much higher stability in time. As you can see, this is the pure three-dimensional material, and these below are the mixtures. Another strategy has been the one to really fabricate colloidal quantum dots with these systems. And actually, the system then at the nanoscale become stable because the surface help to relax the lattice parameter that actually give the structurally instability. So this is very interesting because it means we have some strategies to stabilize the system. Another important thing I want to discuss is the fact that many of the devices that are fabricated at the moment in the laboratories, and many of the devices that give rise to records, actually they're fabricated by spin coating. So spin coating is a technique that is very easy to implement in a lab scale. However, it's not very easy to scale it up, in particular when you want to go to a production of solar cells. Other two techniques that instead they are very scalable are the evaporation technique, that is depicted here on the right, and another technique that is using also solution processing, that is the slot die coating or Dr. blading technique. So these last two actually should be more implemented in our research in metal halide perovskite. Now, what is the point? How we can fabricate this formidaminium lead triiodide in the black phase, and how we can do it by a scalable deposition technique. Before I explain you how we did that, I want to introduce our 2D perovskite systems. So actually, you can open the structure of your perovskite, for example, using this phenethylammonium iodide ligand, and then you will get this phenethylammonium lead I4 stoichiometric formula. And actually, you will get some sort of quantum wells, because you will get some the inorganic octaedra that are separated by two layers of these phenethylammonium molecules. So this obviously gives rise to a two-dimensional system. And actually, it is really a quantum well system where electrons are delocalized in the planes of composed by the inorganic octaedra. These systems are extremely stable thermodynamically, more stable than the three-dimensional one. And actually, when you try to deposit them from a solution, and you use, for example, a technique as a blade coating, you can get very easily oriented the film where the inorganic planes are parallel to your substrate. And this is a demonstration with a beautiful Dvorak's image showing how well oriented are the films. Now, what we develop a technique where actually we started from a two-dimensional film, so from this phenethylammonium lead iodide, we deposit it by blade coating, and obtain very crystalline two-dimensional films that are depicted here in the figure that is called the B. After obtaining these two-dimensional films, actually we immerse them in a solution containing the small organic cation, the formamidinium cation, into an isopropyl alcohol solution. What is happening in this dipping process, and unfortunately the animation is not working, what is happening in this dipping process is that the long phenethylammonium cations are going out of the structure, and the small formidaminium cations are coming into the structure, transforming our two-dimensional film in a three-dimensional formamidinium lead triiodide black phase. What is very interesting is that actually the films that are obtained, they are unstable if the converted film are not washed by clean isopropanol after the process. Now let's look at what is happening. So our two-dimensional perovskite has actually quite a narrow band gap. It has a photoluminescence emission around 530 nanometers. And we did an in situ experiment, a photoluminescence experiment in situ, where we monitor actually this conversion phenomena from the two-dimensional system to the three-dimensional system. So we have practically our slab of two-dimensional material in a cuvette, and then we started to add the small organic cation, the formidaminium iodide. As you can see, in a few seconds, actually the photoluminescence of the two-dimensional system disappears, and a new photoluminescence peak started growing. And this is the peak that is the signature, the photoluminescence signature of our formidabinium lead triiodide. So this is very fascinating and is very interesting, in particular because the converted film keeps the same crystallographic orientation of our two-dimensional film. So practically, we have here some scanning electron microscopy micrographs these are the secondary electrons on the left side, and on the right side is a backscattering image. And you can see that the two-dimensional material actually grows with a very large crystallites on several microns of dimensions. As I show you at the beginning, these are extremely crystalline. So you can think that practically you have in the vertical direction a single crystal. So when we immerse them in the formidabinium iodide solution, we get our three-dimensional converted film that are also showing quite a nice morphology. We just increase the numbers of pinhole on the surface. Makes quite sense as the long organic cation has to leave the structure at a certain point. And in the last row, I show you what you can obtain by using the same technique, blade coating, to deposit directly the three-dimensional perovskite. So actually it's extremely difficult to make good films of this material because the material tends to crystallize very fast to make these very beautiful structures. Here we have a diffraction pattern of the reference sample and the converted sample. And actually you can see what I was mentioning before, that the converted sample has the same identical orientation of the two-dimensional one. So you see much less diffraction peaks of this, let's say, reference sample, because the reference sample is much more polycrystalline and there's many different orientations. Now, it's also interesting to have a look with the laser scanning confocal microscopy to see how our film look like. And this is somehow surprising because when we look at our two-dimensional film, and please remember this is now in grayscale, but I'm imaging the photoluminescence of the sample, and the light color means brighter photoluminescence, and darker color means weaker photoluminescence. So our two-dimensional sample actually, it looks like it has a kind of mosaic structure with some crystallites that are more bright than others. And actually, I will discuss this type of structures and in the second part of my talk. While our reference sample, as we saw also in the SEM, has a lot of crystallites oriented in very different directions, so we can also see it in the photoluminescence, in homogeneity, while our 3D converted sample, as you can see, it has some inhomogeneities due in particular to the edges of the grains. Now, the conversion works pretty well, as I show you. So this is also the demonstration of the absorption. This is the red is our converted sample. We see the variation of band gap, and you see the two-dimensional perovskite as it is a very peculiar, very strong excitonic peak that disappear upon conversion. What is interesting also that the converted sample, respect to the reference sample, is in general very high quality. Not only it is much more oriented crystallographically, but it has also much stronger photoluminescence intensity, also an indication of the high quality of the sample. What is also interesting is that the converted sample are more stable in ambient condition, and respect to the reference sample. And this is actually understandable because the reference sample has much more grain boundaries that are weaker to the attack of ambient components such as oxygen and the water that are actually degrading the perovskite. So here you can see what is the effect of the degradation in the absorption spectra. So the reference samples practically they die very fast. I will say after 2 days the sample is already very degraded, while the converted samples actually they can be considered pretty good even after 15 days. So here we report the photoluminescence of these samples in time. So these measurements are made exciting with 400 nanometers, but in ambient conditions. So it was another check to see how stable are the samples. What you can see is that the reference sample actually degrades very fast because the photoluminescence change after 30 minutes. There is a new peak around 600 nanometer. And actually it is the indication that lead iodide is appearing as a decomposition product of our formidaminium lead 3 iodide. Instead, the converted sample, as we saw also, let's say visually, are much more stable. And after 30 minutes of excitation in air, well, they decrease their photoluminescence intensity, but they only show a very minor signature degradation with a decomposition around 600 nanometer. So before I want to summarize this part, telling that, well, I show you that actually you can use doctor blading to deposit a two-dimensional perovskite. In particular, in this case, I show you phenantyl ammonium lead I4. And you can use this two-dimensional system as a template, not only to obtain the three-dimensional formidaminium lead 3 iodide, but also to obtain a very well-oriented sample that also display much higher stability to ambient conditions. And especially for me, it's very important that the templating process, because of course we expect that transport properties and actually they depend very much on the orientation and on the quality of the orientation of our films. Also very important is that the sample, they become much more stable. And it is indeed interesting to understand why. Could be a minimization of the surface respected to the volume due to the fact that we are perfecting the crystallinity of the system. We have not any more polycrystalline grains, but could be also the presence of still organic molecules on the surface of the system, of the phenantyl ammonium molecules on the surface that are protecting from ambient conditions. Now, I want to, so while I was discussing this transformation from the 2D to the 3D, actually we noticed this image in the confocal microscopy of this kind of inhomogeneities in the photoluminescence, this kind of mosaic-like pattern. And as we didn't expect this, because the films are of very high quality, as you saw from the diffraction pattern from the GVAX measurements. So we would expect, and also the SEM shows a very flat surface, we would expect something much more homogeneous. So we were intrigued by this mosaic structure, and we started to do some more optical investigations to understand the reasons for that. So here again on the top row, I show some laser scanning confocal luminescence, and the images are just scaling up. They are just, we are zooming in, so the red area will become this one, and this is even a larger zoom out. where you can clearly see that we can recognize the crystalline grains in the photoluminescence microscopy, and but still inside the grains, so there are these inhomogeneities of very bright patches of photoluminescence and a bit more dark surrounding. Now, in the row below, I'm showing first the green image is a wide field photoluminescence image, so just exciting with a ultraviolet lamp the sample. And again, also in this image, you can notice that indeed the photoluminescence has some inhomogeneities, so it is bright patches. Now, of course, the first thing we have been thinking was that these inhomogeneities could be indications of crystalline orientation. So then we did some transmission microscopy with different polarization. And indeed, we saw some little variation by changing the polarizer orientation. However, it doesn't look like that the bright spots, so here actually you can see that the image, the photoluminescence in wide field, and the two transmission different polarizer angles are done on the same spot. So actually there is not a one-to-one correlation of the bright region with, let's say, polarization difference due to crystallographic orientation. So then we had to go a little bit deeper, and actually we tried to, what we did spatially define photoluminescence. So actually, we go through the confocal microscope. We first do by scanning, we measure this image. Then we select the spot we are more interested in. We practically park our laser on a specific spot. And now, so practically the laser will scan on a very small area, generally around 1 micron squared or even lower. And then we can go to do some spectroscopy. So namely, this is the steady state photoluminescence of the spot, of the bright spot, here called A. And here we have in red the steady state photoluminescence of the spot B. Well, what we learn is that indeed is not a different material. So it's practically the same identical photoluminescence spectrum, as just the intensity is magnified in spot A than in spot B. But now, since we are exciting all this with time resolve laser, actually we can even go to do some time resolve spectroscopy. And again, we measure our decay time in A and our decay time in B. And by doing that, we see that spot A has much longer decay time than spot B. So it appears that indeed there is some non-radiative channels that get open in our spot B. But let's try to understand a bit better what is going on. And so what we did here, we did actually the same laser scanning confocal photoluminescence map. And this time, so you saw this map now already several times. This image is now the top of the, so it's the front surface of the film. And this one instead is the, let's say, the buried surface of the film, the one that is in contact with the glass substrate. So we select a very thin glass, and we succeed to image also our back surface. What is interesting is that our back surface, while we can easily see the grain boundaries and some little inhomogeneities due to the crystallization, it doesn't show the same, let's say, mosaic structure in the photoluminescence that our front surface. So then, of course, this makes us think a lot, because what could be so different in the film formation from the bottom surface and the front surface. And we had an hypothesis that actually the films could be, when we put the components together to form the two-dimensional perovskite, so the stoichiometry could have inhomogeneities along the direction perpendicular to the substrate. So therefore, we did a set of samples where we use different stoichiometries of the phenethylammonium iodide and the lead iodide, that are the components that we are using for the synthesis of the thin films of the material. As you can see here, first in the left side, so these are the samples that are of stoichiometry, because they have too much lead iodide. So the good stoichiometry is 221, so it's this line here in the middle. So the samples that have too much lead iodide, actually they are the less bright one, and they are the one on the left side of the stoichiometric sample. Instead, the samples that have an excess of phenethylammonium iodide, actually they show to be quite bright, or even brighter than the stoichiometric one. So here we can see the photoluminescence spectra, and you can see that indeed the 221 and the stoichiometry with a higher content of phenethylammonium are the brighter one, and when we go out of stoichiometry, so the photoluminescence spectra is weaker. So now, when we go to see, again, our samples, both with the photoluminescence and with the SEM, and here I have to apologize because the label here on the side, on the left side, is wrong, so they are inverted. So the top sample is out of stoichiometry, so he has a 1 to 2 composition, so he has an excess of lead iodide, and it gives rise to these very dark spots, the very dark crystallites. When you look at them with the SEM, is clear that they are crystallites. While the stoichiometric sample, again, he has this typical mosaic-like structure of the photoluminescence, but it has a very flat surface. Interesting is that when you go to look at the diffraction pattern of these two samples, the stoichiometric one has the diffraction pattern that you expect, while the one out of stoichiometry show lead iodide impurity, as we expect from the composition we are using. So it seems that, so actually we have a kind of a gradient of stoichiometry in our samples, and this could be the reason of our mosaic-like photoluminescence. Now we went even further to investigate these films, and now we did, let's say, spatially resolve photoluminescence, but also we lowered the temperature. So here you can see we did measurements from 350 Kelvin, 250 Kelvin, and 4 Kelvin. What you can notice from the photoluminescence maps is, first of all, that the mosaic structure is disappearing when you go to low temperature. So the sample is becoming much more homogeneous and even brighter, as we expect when we bring a semiconductor at lower temperature. So here we see actually a very nice experiment Herman did, where he succeeded to keep under the focus the same identical area of the sample, and he went from room temperature to 10 Kelvin, and he performed time resolve measurements in 2 points, one bright room temperature and one dark room temperature, and he compared the same identical points at 10 Kelvin. And actually what he found out is that what is bright and room temperature it stays very bright at low temperature, and what is dark room temperature, actually it becomes quite bright also at low temperature. So the sample becomes very homogeneous when the temperature is lower. Of course, we put this data together, so the ratio of the darker points and the bright points versus temperature. And as you can see, the measurements were done in a very systematic way, and we came up with an activation energy for our, let's say, dark photoluminescence. And the activation energy is 0.4 electron volt. So actually what we are seeing that a room temperature, so we have some very effective traps that make our sample dark. Now I want to finish giving a positive touch. Yeah, the sample has a mosaic-like structure, and is probably due by inhomogeneity in the stoichiometry. However, if it is an homogeneity of the stoichiometry because we have a low amount of phenantyl ammonium iodide, then we can try to passivate our samples by putting some extra phenantyl ammonium iodide on the surface, just by, for example, spin coating some phenantyl ammonium iodide on top of the surface. And actually, it is very interesting that indeed it works. The photoluminescence after, I think it was an immersion on the phenantyl ammonium iodide, it becomes much darker, much stronger, sorry. So we have almost a 50% increase of the signal after 10 minutes. You can also see the effect on the photoluminescence maps. And here, actually, it is a distribution of the photoluminescence intensity per pixel. So these are the number of pixels that have a certain number of counts over the image. So showing that indeed the image altogether becomes much more bright than it was after the treatment with the phenantyl ammonium iodide. As a last evidence, we have that actually the lifetime, it is actually not changed, but because of the photoluminescence intensity is increased, so it is indeed a time zero phenomena. So it's something like an increase of the population of the excitation very short time. So now let me summarize. So I show you, I hope, that the stoichiometry of the precursors influences not only the morphology of the sample, that is something that is rather well known in the literature, but also very much the photoluminescence and the amount of defects in the sample. An excess of lead iodide is actually very detrimental for the quantum yield of the photoluminescence. And what is more interesting is that even if you started from a stoichiometric solution, locally you might have regions of your sample where you are out of stoichiometry, and you create defects and you create quenching of your photoluminescence. So there is a non-radiative channel that is thermally activated, and actually the energy is wrong. It's actually pretty high, it's about 400 millielectron volts. Interesting, we can solve a little bit of the problem by a post-treatment, passivating the surface with a long organic cation. With this, I would like to conclude. I would like to thank the two people who have been behind all the work that I presented. So now, so there are Samson Adjocaster, now Dr. Adjocaster, and Herman Daum that is also completing the PhD very soon. And with this, I would like to thank you for the attention.
Thank you very much, Professor Mara. Thank you very much. That was very interesting. We will now go ahead and take some time for questions. Just a reminder, please be sure to type your question into the question box in your control panel. Maria, I have one first question. So we have, in the conversions from 2D to 3D, can we exclude that 2D domain are absent?
Yeah, so this is quite interesting. To be frank, I cannot fully exclude it at the moment. So maybe I can go to the slide. I don't know if the public will see when I go to the slide. So what we know is that we don't see any trace of the 2D perovskite in the photoluminescence. Of course, the 2D perovskite has a much higher band gap than the 3D perovskites. So in principle, if will be there, you might eventually be able to see it, just because it will appear as a higher band gap photoluminescence. Of course, you have to be careful because there is also, you could have also very effective energy transfer from the 2D to the 3D perovskite. So the other, so we don't see it optically, but I'm still convinced there might be some 2D perovskite around the sample, maybe just a monolayer of the organic cation. Also because what we see about the stabilization. So the sample become extremely more stable than so the reference sample. And also we know that this sample is very structurally very unstable. It tends very fast to go to the yellow phase in ambient condition, and instead in our case it doesn't do it very fast. It does it probably in 20 or 30 days. So it started to become a bit more faint around 20 days.
Okay, thank you for this answer. We have another question. Have you measured the time result photoluminescence for the 3D converted FAB3 film? Is it comparable with the reference one film or the single crystals? And for the second half, the PAA surface passivation, how is the film morphology? Can the enhanced photoluminescence from morphology change, which may result in some waveguide effect?
Okay, the first question, if I understood correctly, is asking if the lifetime of these two samples, the converted one and the reference one, is different. I understood that correctly?
Yes.
Okay. Yeah, I don't have the measurement here, but if I remember correctly, is much longer, the one of the converted one. And yeah, in agreement with also what we see from the quantum yield in general of the sample, it becomes much more bright. The second question, I don't remember anymore.
About the surface passivation, how is the film morphology evolving?
Yeah, it's a good question. I don't have a measurement here, so I don't have the SCM measurement. I have just the confocal measurements here. I don't expect, actually, we did quite some work on trying to passivating surfaces. In this case, because the confocal is not telling me that I'm changing much of the surface, I expected that actually the surface stays pretty flat, like we started with. In other cases, we did some work on passivating three-dimensional single crystal of methylammonium lead tribromide, and there, depending on the agent you use for the passivation, you can also see etching along a certain crystallographic direction. So indeed, you have to be very careful with passivation because sometimes you can also strip away parts of the sample because of in certain directions.
The last part of the question was actually asking about if it could induce some waveguide effect, actually. So you...
Waveguide effect. Well, but these films, indeed, I think they are very good. They could have a good waveguiding effects because the surface, they are very flat, in particular the two-dimensional one. As I show you, they have... of course, it depends by the refractive index. But yeah, they have a very good surface. They are very flat and they are very crystalline. So I think they are, even without treatment, they are good waveguides.
Okay, thank you. Thank you very much. So that's all we have time for today. Again, thank you very much. That was very interesting. All the unanswered questions will be answered individually by email. We appreciate you being here. A recording of this webinar will be available in our Learning Center on our website from next week on. Please make sure to check the website and get in touch if you have any further questions. Thanks again for joining us today, and please enjoy the other presentation on offer. Thank you very much. Bye.
Bye.
Bye.